Alright, so we're going to get into Chapter 7 now, starting off in 7.1, which is on gases and gas laws. Alright, so when we talk about a gas, let's go back and talk about basically what that looks like. If we picture a gas in a container, the gas particles fill the container. They're moving around randomly. They're colliding with each other. They're colliding with the walls of the container, so on and so forth. Now, as they collide with the walls of the container, they exert a force on the walls of the container. We call that force pressure. Right? Now, if we think about this, so first of all, we can measure that force, and that's one of the things that we can use to characterize a gas. But also, if we think about this, okay, pressure comes from gas molecules colliding with the walls of the container. So if we do something to make them collide more often, then we're going to increase the pressure. If we do something to make them collide with more energy, then we're going to increase the pressure. So anyway, bear that in mind. All right, we have a couple of units that we use to measure pressure. One really common one that you may have seen, just for example, on your tires is the PSI. That's pounds per square inch. Pounds per square inch. Normal atmospheric pressure is 14.7 psi. Now, just for convenience sake, we have a unit that we use quite often in chemistry for pressure, and that unit is the atmosphere. Normal atmospheric pressure is 1 atmosphere. We can also talk about we also have pascals. A pascal is 1 newton of force. Newton is about 1/4 of a pound, so 1 newton of force acting over an area of 1 square meter. Normal atmospheric pressure is 101,300 pascals. And then our last one is one that's actually really common in a lot of settings, but it's a little bit of a strange one at first. And it goes back to the days of measuring atmospheric pressure with a mercury column barometer. So if we have a tube, we fill it with mercury, we invert it into a dish of mercury, leave that open to the atmosphere, and we measure this height here. Normal atmospheric pressure is going to be 760 millimeters of mercury. Right? So that's where that comes from. All right. Now, when we talk about gases, though, in this section, we're kind of going to get straight to the point with this. Excuse me. And we're going to talk about gas laws. Gas laws relate changes in pressure, volume, temperature, or amount of gas to each other or to a constant. All right? We're going to just go through a bunch of these. Right. Now, I'm going to give you names for these laws, but I don't actually care what those names are. Okay? We give the names just because your book uses them, and also they have been used historically, but really we don't care about the names of them. We just care about being able to use them. Right, so first of these is Boyle's Law, which relates pressure and volume to each other. Right? Boyle's Law takes the form of P1V1 equals P2V2. Right. What does this tell us? Basically, this tells us that if we decrease the volume, the pressure increases. All right? A lot of times when I'm talking about these examples, I like to talk about balloons. Okay? Let's say that I have a balloon where the pressure in it is 1.2 atm, and that's at a volume of, let's say, 750 milliliters, right? And then let's say that I decrease that volume to 500 milliliters, right? So that's going to be my P2. That leaves, I'm sorry, that's not my P2, that's my V2. That leaves P2 as my unsolved, as my unknown. All right. Excuse me. So we're solving for P2. Let's rearrange this. P1, V1 over V2 equals P2. All right. So 1.2 atm, 750 milliliters over 500 milliliters. Look at this. Our milliliters are going to cancel. That's going to leave us with atms. And we get P2 equal to 1.8 atm, right? That's Boyle's law. Our next one is Charles's law, which relates volume and temperature together. All right. This is one, there again, let's go back to a balloon. I always like to think of this with a demo that I used to do at demo shows where I would have liquid nitrogen in a cooler and I would try to stuff as many balloons as I could into it. So let's say that I start with a balloon with a volume of 500 milliliters and a pressure of 1.1 atm. I don't care about the pressure. Pressure doesn't appear in this equation, so but that is sitting at a temperature of, let's say, 22 degrees Celsius. And let's say that I put that in liquid nitrogen, which is about minus 200 degrees Celsius, right? Now, to solve this, we have to do, actually let me backtrack. This is going to be my T1, this is going to be my T2, this is going to be my V1, this is going to be my V2. Right, so if I want to rearrange this to solve for V2, my quickest route to that is going to be to cross multiply, so V1 T2 is equal to T1 V2, V1 T2 over T1 is equal to V2. All right. Now, here's something else important with this. When we deal with temperature in a gas law problem, we have to have that temperature in Kelvin. All right. Temperature must be in Kelvin. So let's convert this. 22 plus 273 gives me 295 Kelvin. And this is going to be 73 Kelvin. Okay. So let's plug these in. .500 milliliters times 73 Kelvin all over 295 Kelvin. And that gives me a V2 equal to 123 milliliters. Right? Now, we also have the Gay-Lussac law, which relates pressure and temperature. So P1 over T1 equals P2 over T2. Right? Basically telling us as temperature decreases, pressure decreases. The example I always use for this one is your car tires on a cold morning. Maybe you get in and turn your car on and your car tells you that your tires are low. And let's actually, just to go with that, let's solve that. All right? So, let's say that we air our tires up to 35 psi. By the way, units don't really matter on this as long as we're consistent. Okay? But let's say we air our tires up to 35 psi. And we do that on a warm day. Let's say that we do that on a day, I'm just going to go straight to Kelvin. Let's say that I do that on a day that's 300 Kelvin. Right? And then all of a sudden the temperature drops a whole lot. And it's, let's say, minus 15 degrees Celsius, which is going to be a T2 of 258 Kelvin. All right. So, let's solve for our T2. I did way too many steps for the last problem to solve for T2. I really can just multiply both sides by T2 and I get P1 T2 over T1 is equal to P2. All right. So that's going to be 35 psi. 300 Kelvin over 258 Kelvin. And we get we get 30 0.1 psi. All right? Now, the gas law I will provide you on the exam is the combined gas law, where basically we just stick all of these together. P1 V1 1 over T1 is equal to P2 V2 over T2. Right, now, you can get any of these others out of this. If you're not provided a volume, just for example, take volume out. P1 over T1 equals P2 over T2. Or if you're manipulating multiple variables. Alright, let me go on though and do the ideal gas law. Right? The ideal gas law is probably the single most important gas law that we're going to talk about in here. And we can actually derive all of these others from the ideal gas law. The ideal gas law relates pressure, volume, amount of the gas in, which is number of moles, and T all together through a constant, R. T is temperature and R. And I wrote it like that just because as I was speaking it. Normally it actually takes the form of PV equals nRT. Right? Now, our value, we could calculate a value for R for any given set of variables, or I'm sorry, for any given set of units here, as long as our temperature is in an absolute scale. Now, of course, Kelvin is the absolute scale that we use in here. There is one other one out there, but for our purposes here at temperature, we're going to assume that there again that we always do this in Kelvin. But anyway, the value that we use for R is 0.0821 atmosphere liters per mole Kelvin. Alright, so let's say that I have let's say that I have 16.2 liters of a gas at 295 Kelvin and 1.3 atm. How many moles? Right? So in this one we're solving for N, it's going to be PV over RT. Okay? Is equal to N. So 1.3 16.2 liters over 0.0821 atm liters per mole Kelvin times 295 Kelvin. It's ATM. We look at this. ATMs cancel, liters cancel, Kelvins cancel. And we get N equal to 0.86 0.95. So that covers our gas laws.